Hello everyone, and welcome to an exciting webinar. We are very happy to see you all joining us. And today's webinar is about an important new development in concentrator design. It uses advances in isomeal and Jamison cell to deliver a step change in concentrator performance. We have two presenters. The first one is Glenn Stipper, our technology manager for mineral processing. From Glenn, you will learn the basics of the new plant, and you will also hear from two operators that we are about to adopt the new concentrator plant. Then we will have Matt Dunn, our senior metallurgist, and he will be presenting some of the circuit design principles and changes to the two technologies, isomeal and Jamison cell. This webinar will be recorded and the link will be sent to you in the near future. We invite you to submit your questions during the webinar by using the Q&A function. Some questions will be answered during the live Q&A, and all questions will be answered in full by email, so please be patient. Thank you, and let me pass the microphone to Glenn.
Thanks, Erica. We're at an exciting period with our technologies at the moment, particularly with our mineral processing. And today I would like to talk about two projects in particular that we think are significant for the industry and obviously for Glencore Technology. So I'm excited to announce that Glencore Technology has been awarded the contract for the supply of a full circuit Jamison cell and isomeal circuit. This is a large lead zinc concentrator, and it's potentially the largest lead zinc concentrator to come online in the last 40 years. It will be treating a design treatment rate of up to 175 tons per hour. And pretty much it's a replacement of 63 conventional cells, conventional tank cells with 19 Jamison cells. So this is a significant reduction in footprint, roughly half the footprint, and also roughly half the power as well. It's also, the building itself is also a much lower profile, so there's a reduction as well in the height of the roof, as you can see here in the picture below. Sorry. Below, where you can see here that because there's no agitators to lift from the Jamison cells, it means that the height of the building and the crane can also be heavily reduced. As part of this project, I'd also like to announce the new isomeal we are bringing online, which is the M20000, a 5 megawatt motor. For this project, we will be supplying 3 of these. And again, the footprint, the horizontal footprint, the low profile of these isomeal complements the low profile and height of the building for the Jamison cell circuit. So commissioning for this plant is relatively soon. So we're looking in early 2023, or if things go well, potentially even in late 2022. So you won't have to wait long for the circuit to come online. So I just want to quickly now flick across and just show you just a 3D indicative model of what the circuit looks like. Okay, so as you can see here, the circuit, just try and fly around here. So down the end here, the far end, you can see that we have the isomeals positioned. If I can just get my steering right. So we have the 3 isomeal M20000s down this part of the circuit. 2 of these will be servicing the zinc, and 1 of these will be servicing the lead concentrate. So these are rougher concentrate regrinding. The approximately 400 tons of zinc pyrite concentrate will be reground on this side in the zinc down to approximately 10 to 13 microns. And on the lead side, there will be around about 130 tons an hour, regrinding down between 7 to 10 microns. So it is another fine grinding application. So if we move along the circuit now a bit closer, some of the keys to the design is that you'll notice that we don't have any standby pumps. The standby pumps are on the main transfer components, but when it comes to the actual Jamison cells themselves, these have a very high efficiency in terms of the way in which these pumps can be operated. We also have a unique bypass, so any cell in this unit can actually be bypassed very quickly, and that pump can then be transferred straight out and then another pump drop back in. So the impact on the circuit is very, very little, and it means that the operation can keep functioning at a very high level. The access to that in this design is basically from the, sorry, steer around this, is based on the overhead crane. So we have access on each one of these from overhead cranes on either side of the circuit. Oop, I can't really get around that. So just a quick overview of the actual circuit. So on this side here, we have two lead rougher scavenger Jamison cell. These are our large Jamison cells, our new ones to the market, the B8500 12 downcomer. So this is something that Matt Dunn will talk about in a little bit more detail later in the presentation. So these two circuits here then have feed into the lead cleaning circuit in here. On the other side here, we have 5 of our large rougher scavenger for the zinc pyrite flotation. So this is a large mass pull application. Once the concentrate is passed through here and reground to a fine level, then it passes through 11 of these B6500. So these are currently our largest installed Jamison cells in the market, and we have over 100 of these installed. And through here, a certain amount of this part of the circuit, so 6 of these is dedicated to the pyrite rejection, whilst the remaining ones, 3 are dedicated to just upgrading the final stages of the zinc concentrate. Okay. Okay, so just wanted to quickly now touch on, what I wanted to do is actually now have a discussion with Alexander Konetsky. So he is actually the chief metallurgist for Ozorno, and he's agreed to come on here and have a discussion regarding this project. I'd also like to introduce Anya Petrosky. So she is the business development manager for the CIS region, and she will help translate for Alexander.
Alexander, добрый день.
Добрый день, Анна. Добрый день.
So welcome both of you. So the first question I have for Alexander is the new circuit is roughly half the size of a conventional circuit. So what other 2 or 3 benefits do you see in the selection of this technology?
Александр, вопрос от Глена. Новый цикл, он будет примерно в 2 раза меньше цикла на традиционных фотомашинах. Какие 2 или 3 других преимущества для вас важны были при выборе технологий?
Коллеги, добрый день. Для нас важны следующие преимущества, которые я хотел бы отметить. Первое – это снижение общего количества флотационных машин с 63 штук пневмомеханического типа до 19 флотационных машин Jamison Cell. Второе – это значительное сокращение объема строительных работ. У нас получилось примерно на треть. Третье – это существенное сокращение операционных расходов. И, наверное, четвертое – это, в принципе, легче работать и проводить обслуживание при меньшем количестве единиц оборудования.
There are several points, Glenn, which Alexander highlighted. The first one is the reduction of the total number of the flotation machines from 63 pneumatic mechanical type cells to 19 Jamison cells. The second advantage, which was considered, was a significant reduction in the volume of the construction works. It's almost 3 times less. The third advantage is lower operating costs, and the fourth one is easier to operate and maintain less units.
That's great. And so another question is how important is the minimizing the maintenance and downtime? And do you believe this new concentrator will minimize them?
Александра, насколько для вас важны минимизация времени на их техническое обслуживание и простои? И вы полагаете, что новый цикл флотации сведет их к минимуму или же нет?
Да, конечно, важны. Jameson Cell не требует, в принципе, остановки для технического обслуживания. Ну и также с циклом на функционных машинах Jameson Cell будет дополнительное преимущество в части складирования меньшего количества запасных частей для оборудования.
Glenn, of course, these are important. Jameson Cell doesn't require shutdown for maintenance, which means no downtime. And also with Jameson Cell, the circuit will have the added benefit of storing fewer spare parts.
Yes. Yeah, I think that's a great point, because of the Jameson cell has very few moving parts. There's no agitators or stators or that sort of thing. So it means that storage and maintenance is a lot less, as well as inside the concentrator building, also out in the maintenance as well. So just another question, what do you think, or I suppose, what do you think this project will contribute to the future design of concentrator buildings or operations?
Александр, следующий вопрос. Какое место, по вашему мнению, займет новая схема в будущей тенденции разработки проектов фабрик?
Я думаю, в связи с истощением минерально-сырьевой базы и стремящейся тенденцией к снижению крупности ценного компонента в рудах, схема переработки озерного месторождения, наверное, будет флагманом в области обогащения таких труднообогатимых и трудновкрафтных руд. И, наверное, не только в России, а во всем мире.
Glenn, due to the depletion of the mineral resource base and the tendency towards a decrease in the size of the valuable component in the initial ore, the project Озерное Deposit Processing Flowsheet, it will probably be the flagship in the field of complex, finely disseminated ores enrichment, and not only in Russia, in the whole world.
Okay, that's good. And another question is, how important was the multi-commodity mineralogy or the complexity of the ore in your selection for the isomill?
Александр, следующий вопрос. Насколько важно было ваше многокомпонентное питание при выборе мельницы isomill?
Да, было важно. Мы анализировали опыт и Маунтайза, и МРМ, сверхтонком помоле и флотации свинца и цинка. А также хочу отметить, что узкий гранулометрический состав продуктов изомил с получением меньшего количества сростов. Также доказанная эффективность этой технологии играли определяющую роль в выборе до измельчения.
Glenn, yes, it was important, and they have analyzed Mount Isa and MRM experience with ultrafine lead and zinc regrinding and flotation, as well as narrow particle size distribution in the isomill, meaning less composites, and also proven efficiency were one of the key factors in technology selection.
Yeah, thanks, Anya. Yeah, I mean, that's, I suppose, another good point. The isomill was developed for the lead zinc, the complex ores for Mount Isa and MRM. So it's very, I suppose, the purpose is for lead zinc in the past, but what it was designed. So just one last question, Anya, is when is the installation and commissioning schedule due?
Александр, и последний вопрос. Когда планируется монтаж и пусконаладочные работы?
Как у нас поставка планируется во втором квартале 2022 года, то есть фактически через год. А монтаж и пусконаладочные работы мы хотели бы выполнить до середины 2023 года. То есть вот эксплуатацию фабрики, это, соответственно, третий квартал 2023 года.
23. So full plant commissioning is scheduled for the third quarter 2023. Flotation complex delivery to site is planned in the second quarter of 2022. And obviously installation and commissioning works around mid-2023.
Okay, thanks, Anya. Well, thanks very much, Alexander, for your time, and I suppose the opportunity to work on this project as well. And I think it's going to be a very exciting project moving forward. So thank you. Thank you both.
Александр, спасибо большое за интервью.
Да, не за что.
Thanks, Glenn.
Okay, so now I would like to actually introduce another exciting project that we have, which is the New Britannia Hud Bay circuit. Now, some of you may already be aware of this, but it's in Canada. It's based in Canada. It is again a replacement of a conventional circuit. So it's a 70 ton per hour circuit, copper concentrator, and it is 100% Jamison cells. So it's a reduction of 11 conventional cells down to 4 Jamison cells. So not quite the same scale as the Ozorne project. However, it still represents half the footprint reduction and also power. This circuit is due for commissioning actually the later part of this year, so in Q4. So it's going to be a very exciting project, and also you don't have to wait long to see the results of this. So just some quick photos here. This is just of the installation occurring. This was about 2 weeks ago, so you can see that the installation is in progress. So I just want to, last week we had an interview with Matt Taylor. So he is the process manager for Hud Bay, and he agreed to have a chat with us, and we recorded that now. So I'm just going to play that recording quickly, and he'll talk about some of the benefits that he saw with this plant.
I'm interviewing Matt Taylor, Metallurgy Manager for Hud Bay. New Britannia is, of course, executing a full circuit of Jamison cells. Matt, what are the top 3 reasons you selected Jamison cells over other cells?
Well, the first reason is it comes down to the ore we're treating. So the Lalor mine in Snow Lake that we're going to be processing ore from has 2 types of ore. It has base metal ore, which is rich in pyrite, above 20% pyrite in feed, high zinc, lower copper, and lower precious metals. In the other type of ore that's in the Lalor mine is the gold zone ore. So it's much lower in pyrite, so below 4 to 5% pyrite compared to the 20% in the base metal. And also it's got a lot lower other base metals in there. So zinc, there's literally no zinc to talk of. It might spike to 0.5, 1%, but no valuable carry of zinc there. But it has copper in there as well, and high gold, so above 5 grams per ton gold. So that's where the ore is coming from for the New Britannia circuit. But within the gold zone, there's actually 2 types of ore in the gold zones. There's a low copper, high talc portion. It comes from our zone 25. And then there's a low talc, high copper portion. It comes from our zone 27. So zone 25 is 0.2 to 0.5% copper. You can have anywhere up to 10% talc. And whereas our zone 27 is very high in copper, above 2% copper and no talc really to speak of. So we needed a circuit that could handle wide swings in head grade. So a standard mine plan will say we're getting 50% from zone 25, 50% from zone 27. Your average head grade will be 1%. But we know in reality it's not like that. So we could have very wide swings in head grade from below 0.5% to above 2% in hours in the day, not over days or weeks.
Right.
So we needed a flotation cell that could actually handle large swings in head grade and give us the ability to handle it robustly and also quickly. So when we were designing the original circuit with mechanical cells, one of the questions was, how do we actually account for this problem?
Yes.
So how do we crowd or not crowd, mechanical rougher cells? How big do we make our cleaner circuit? So do we design it in the midpoint? So sometimes our cleaner circuit's too large, so the residence time is too large and we don't get selectivity, or we have a cleaner circuit that's too small and we don't get high cleaner recovery. So how do you combat that? So choosing the Jamison cell for all our cells kind of solves that problem because it has a large range in carrying capacity. It has wash water so it can clean on every cell. And the configuration we've chosen for it allows us to use the first cell to produce final con. So the other factor in this ore is it's highly liberated at the selected grind size, so above 85% liberated. So when con grade is high, we can turn the first cell into a scalper and produce final con directly from float feed. And that gives us the ability to deload the cleaner Jamison cell. Conversely, if the head grade is low, we can close it up and send that to the cleaner circuit for further upgrade. So having that ability to wash on each cell, large capacity and range in carrying capacity, allows us flexibility to handle the wild fluctuations in head grade.
Yes.
Yeah. The second reason comes to constructability and also footprint. So when we've gone to the Jamison cell, we've gone from 10 to 12 mechanical cells in the original design circuit to 4 Jamison cells.
Right.
And that's been a significant footprint reduction inside that circuit. So I believe the roof has dropped by about 2 meters and the width of the building by about 8. So we've dropped probably about 50% of the footprint for our flotation circuit.
Right.
Just by selecting Jamison cells. So that has been a significant saving in cost.
Yes.
Yeah, exactly. And then the final reason comes down to controllability. So it's much easier to control four flotation cells, each of them doing a distinct duty, than controlling 10 or 12 mechanical cells, where, say, within a bank of rougher cells, you're trying to control 5 or 6 roughers individually. So you've got much more instrumentation and P&ID and airlines and all those sort of things that go into their cells, whereas we've got 4 cells to control. And we're not worrying about, did we pull too much mass off the first rougher, so we starved floatable material on the last rougher, so there's not enough material to actually form a froth. Yes. There's none of those issues because we've got 4 cells. It's a lot simpler approach to control.
That makes perfect sense. Second question, Matt, this is only the second full Jamison cell circuit in base metal since 1996, when Jamison cells moved focus to coal for a time. How did you mitigate any concerns during technology selection?
It came down to we piloted it, started, so we got the on-site team comfortable with it. So we have a nearby concentrator, the Stall mill, which is processing the base metal ore from Lalor. So we actually got the L500 rig. We got, at the time, Virginia Lawson. She came to site, and we ran the L500 on multiple different streams within our Stall concentrator, and actually got everybody familiar with the technology. That was a big step in showing that, look, it actually works. It's not this boogeyman type of thing that's, this technology from Australia doesn't work in North America. You kind of can get those comments from time to time. Different areas of the world have their technology that they use. Yes. I think a famous one would be columns in South America. There's, everybody loves their columns. They have their application. Some of them I agree with, some of them I don't. Some it's personal reasons, but you do have that regionality in technology selection. So that was definitely a barrier we had to overcome. But really, for us, it was getting the pole on the site, getting people familiar with it, and getting them comfortable with, yes, this technology actually does work. The second one was also having people in the position of decision making who are experienced with that technology. So myself, I had a leading hand in the design of the circuit and the selection. And I had vast experience with the Jamison cell in Mount Isa, with commissioning the full Jamison cell cleaner circuit in Mount Isa, as well as the Jamison cells at Cadia Valley, where I was the senior project engineer. So part of it was myself being comfortable with the technology, seeing it deployed and what it can do, and then imparting that knowledge and that experience into the organization and giving them confidence that I was confident in it. So that was a big part of it.
Very good. Very good. Third and last question, Matt. Where do you see the future of the IsaMill and Jamison cell technology?
Well, I see it moving further up into the circuit. So most of the deployment of IsaMills and Jamison cells has really been exclusively in cleaner stages. After you've pulled your rougher con, then you put the IsaMill in there, you grind it, and then you use a Jamison cell for either a scalper or a final cleaner. I see it moving further up. So we see at Cadia, they're looking to put one in the rougher circuit. I was involved in that project early on as well, so I'm quite well familiar with it. But I see it moving further up and seeing further applications in the rougher stage.
Yes.
And potentially overtaking mechanical cells in that duty. So moving further up is definitely where it should be. And also in other types of minerals that haven't really seen it before. So well, you look at, say, a copper moly separation.
Yes.
They either use mechanical cells or, self-aspirated WEMCO cells for various reasons. And test work I've seen and done has seen that if you put, say, a Jamison cell as a rougher and a moly cell circuit, you can get very high recoveries at extremely high grades and cut out, 2 to 4 stages of cleaning out of your moly circuit if you put the Jamison cell in the correct application. So putting it into, say, the future of the Jamison cell, putting it into circuits for metals that it traditionally hasn't been in, or it's been in later stages. So it's about moving up closer to the head of the circuit is where I see it. And I see the same for the ISOMIL. So yeah, it's been kind of like focused at anything. You can grind stuff that's fed below, say, 300, 400 microns, but push it up the scale. Can it take SAG mill or AG mill discharge? Can it get fed 1 mil material? Can it replace the ball mill? Because ball mills are efficient enough, but stir mills are another step above efficiency in power applications. So can the ISOMIL displace in certain applications a ball mill? So that's where I see it going, is moving these technologies further up the flow sheet, closer up to where the bulk of the material handling is occurring.
Excellent. Thank you, Matt. Thanks for the time. I really appreciate it.
Okay, so I would now like to hand over to Matthew Dunn. So he is a senior metallurgist at Glencore Technology, and he will be discussing some of the, some of the processes we go through for designing a full circuit, and also some of the latest models that we've talked about just earlier on, and how they've sort of been evolved across our different models. So I'll hand over to you now, Matt.
Thanks, Glenn. Hello, everyone. My name is Matt Dunn. So as Glenn mentioned, one of the senior metallurgists here at Glencore Technology, working in the Jamison cell and ISOMIL space. I'm just going to talk to you today about the Jamison cell and ISOMIL full circuit designs, and try to touch on some high-level information about how we go about sizing our circuits, selecting our equipment, so we can make projects like Zorne and Hudbay possible. Okay, the focus of this segment is to discuss in high-level detail some of the fundamentals of our circuit design. We'll start with going over the principles of the operation that drive the circuit design. We'll then talk about how our circuits are fundamentally constructed. We'll then go through some of the strengths benefits of the full Jamison cells, and finally finish with some discussion on a developing range. Okay, so for our Jamison cell, the principles of operation for these, their pressurised slurry enters a downcomer through a nozzle at high velocity. The slurry jet entrains the air in the headspace, which creates a vacuum, so it's inside here. This draws in atmospheric air through this pipe. So the important thing to remember here is no external blower air supply is required. The jet plunges into the slurry interface inside the downcomer, as you can see here, causing entrained air to shear into fine bubbles. This high intensity mixing leads to high probability of bubble particle collision and contact. And the residence time in each downcomer is only several seconds. Okay, so with these operation principles in mind, we now move to the fundamentals of sizing and cell selection. This high intensity mixing and fine bubble particle interaction drives a fast flotation response. As this is an almost instantaneous process, Jamison cells are not sized by residence time. A real world example of this is shown on the right. You can see an existing tank cell circuit's recovery response over time. So these are individual nodes up to 35 minutes, and the recovery is a function of that. Now look at the Jamison cell point. We can see that a single Jamison cell achieves the same recovery as the tank cell train achieves across those 35 minutes. And this is a good example of the instantaneous responses we see in the Jamison cell and why we don't need to consider residence time for constructing our fundamental designs. When building Jamison cell concept circuits with the isomills included, flotation roughing can be as little as 2 stages of Jamison cells for maximum recovery and circuit robustness. So Jamison cells are actually sized by calculating the carrying capacity requirement of the concentrate. This is the mass of concentrate that can be recovered from a given flotation surface area. It's a function of mineral density, particle size, bubble size, and superficial gas velocity. We also size against volume throughput, ensuring the tonnes of feed and cubic metres of slurry can be physically processed by the specific Jamison cell. The unique advantage of the Jamison cell is its high carrying capacity as a function of its fine bubble size and high surface area and lip length. So now we'll move on to test work functions for this. So to suitably select the duty of our Jamison cells, we can use information obtained from a few different methods. Firstly, our 3-stage dilution test is a great way for sites to get a snapshot of the response of their material using a simple lab conventional flotation cell. Next, we have our lab scale L150, which uses a 20 to 40 kilogram batch of feed and offers direct Jamison cell dynamics to a test. Finally, we have our L500 pilot rigs, which are a great way for sites to test the Jamison cell in their actual process. The machines are rentable units and can be plugged straight into the process to begin test work. So that's similar to what Hudbay did for their piloting. So each method produces data to construct a grade recovery curve. We then use this information to determine where along that curve the Jamison cells will operate. We have a proven record of being able to scale up from 3-stage dilution or piloting directly to the commercial sized units. The graph on the right shows an example of 2 3-stage dilution curves, which you can see here in green and blue, as well as the piloting data shown as the orange dots moving across. We can see that by manipulating the process parameters on the pilot rig, we can work across this grade recovery curve to suit the intended duty. Okay, fundamental circuit design starts with identifying if a final concentrate can be made straight away from the grade recovery curve. If we're able to pull off a final con immediately, then we can employ a rougher scalper, as shown in the example here. So this unit here in this example is producing a final concentrate from rougher feed, and it's represented by this part of the grade recovery curve, where the red line you can see running across the curve is the final con grade target. Following this, we then look to the rougher and scavenger nodes. The objective of these units is to maximise recovery with respect to the design point on the grade recovery curve. We can see in this copper example that we can recover around 60% to the rougher scalper, so around here, to the final concentrate immediately. We then design to recover the remaining 30%, which is the back end of this curve, to our rougher and scavenger concentrates for further treatment. For perspective, in the bottom right, we can see the data obtained from the Jamison cell plotted in green and red against the existing tank cell rougher circuit, which is plotted down here at this black line. Not only was the Jamison cell able to achieve very high recovery from a single stage, it was also able to detect significant volume of gangue material and produce a much higher concentrate grade. So this minimises downstream equipment size and demand as well, which is an important factor. Okay, for the isomill, it's even simpler again. So this is a horizontal stirred mill. It uses ceramic media to grind down particles to produce quite a tight product size distribution. So for the test work's completed on a laboratory M4 or similar isomill. This produces a signature plot, which is what we use to determine the specific energy required to grind down to the target size. The mill is then sized by the energy demand required to grind the material to the desired size at a specific feed rate. The advantage of the IsaMill is that it has proven one-to-one scale up from the signature plot. There's no efficiency factors or correction ratios applied, and the full-scale mill has a guarantee on it. For the IsaMill, there's a wide range of practical flowsheet options available. Typically, the mills are in a circuit with some form of classification, like cyclones. The most common circuit configurations are open and closed. So the example on the right we can see is an example of an open circuit where the IsaMill discharge goes straight through to flotation. A closed circuit would be one where the discharge would return to the cyclone feed and operate in a closed loop. So the IsaMill actually has a great flexibility and is well suited to tertiary grinding, regrinding, and ultrafine grinding. All right, so from what we've just gone through, we can now piece together a concept flow sheet. This example shows a circuit recovering a rougher scalper concentrate, so final concentrate off this first cell, before rougher scavengers recover lower grade locked material to the regrind circuit, as we can see here. The IsaMill regrinds the coarser particles to a desired distribution, with final clean and flotation occurring. Again, we can recover a scalper concentrate from the first stage of the cleaners, and then the tail of this would report to a scavenger or second cleaner, which would perform the duty of recirculating back to the first cleaner, recirculating back to the grinding circuit, or making an intermediate stream, or even making final concentrate as well. So we're now able to build this concept as a 3D model, and here's what it would look like. So we can see the rougher cells here on the left. So our rougher scalper, rougher scavenger. Our regrind mill is here down the bottom with the full plant, and our cleaner cells are hidden at the back. So rough cleaner scalper here and cleaner scavenger behind it there. So in this example, this is a real world case using data. And this example is for a copper operation where they're graded around 0.5 to 1% and it would treat 1,200 tonnes per hour. So some strengths and benefits for the IsaMill Jamison cell full circuits. So the circuits occupy as little as 30% of the footprint versus conventional designs. They have a much shorter vertical height versus conventional circuits to reduce building and maintenance requirements overhead and improve the safety of the operation. So we see a significant reduction in maintenance and operating costs, as we discussed in the earlier examples. So no agitators, rotors, or blowers in the flotation. We use 30 to 70% of the energy a conventional flotation circuit would consume. And the grinding media, so the ceramic media the IsaMill uses, is actually only 10 to 70% of the cost of the higher density media a vertical style mill needs. We also see maximised metallurgical performance. So the Jamison cell flotation is an instantaneous flotation operation, which is extremely advantageous to minimise things like surface chemistry and oxidation occurring. We produce a high concentrate grade, so we remove a lot of gang materials, which not only makes the concentrate grade higher and more valuable, but can also reduce transport costs associated with that material. We produce a tight product size distribution out of the IsaMill as a result of the internal classification rotor. And we have a proven performance across a wide range of size fractions, including coarse and ultrafines. Okay, I'll now move on to our product range development. So what we've been working on recently and our new products that we're offering to clients and some of our solutions. So in the background, we've been working extensively to develop modernised solutions and expand our product range. We now have new additions to both our Jamison cell and IsaMill technologies. The focus for the expansion in the range has been around providing larger units to treat greater throughputs. We are able to offer single one-off units to expand existing sites all the way through to full circuit solutions for not just new projects, but also existing projects. For the Jamison cell, we have our new 8500 12 model. So it's an 8.5 meter diameter 12 downcomer Jamison cell, which comes in both a B and Z type design. The Z type is shown on the right here in this model with the internal recycle mechanism built in. The B type cell is this round structure with an external recycle mechanism. So this box is actually taken away from the side of the cell and placed underneath. So the capacity of these cells is double that of our previous largest Jamison cell, and a single unit could treat up to 1,500 tonnes per hour in some cases. So as Glenn mentioned, one of these Z8500 12s already been sold and installed this year at Cadia. And we're expecting 7 more B8500 12 units committed to the Osorno project. So we've also progressed with design flexibility in some of our products. So modular versions of the 8500 12s, both B and Z, B24s, E8s are readily available. These modular units are segmented in order to minimise the transport size of the various segments. There is a huge advantage to remote locations or transport restricted clients, as these segments they're bolted and they meet a very, very tight transport envelope. So 5 of these modular B24s already exist and have been sold, and we're expecting 11 more to be committed for Osorno. We also have 2 of the E8 modular cells already installed and commissioning around the world. So new IsaMill models for the market. So as Glenn mentioned, we've got 2 new mills that have come out recently. So our M15000 3.8 megawatt unit and our M20000 5 megawatt unit are now available. The M15000 is already installed at Tech's Red Dog site. We have our 3 M20000s committed for Osorno. Okay, our latest IsaMill layout and design options include just the IsaMill only, so just the mill and the mill motor and associated driving equipment. We also have the original IsaMill plant design, which you can see down here at the bottom left. Recent developments of the layout has seen this new design, which you can see on the right, become available, which reduces the footprint of the original plant design. As you can see here on this image on the right, the footprint of this full plant package is actually a lot smaller than a vertical style mill footprint, and it's also a fraction of the height of its competitor as well. So huge advances in not only footprint savings and efficiency, but also mill size and capacity. Okay, thank you all for joining us today. If you're able to please participate in our poll, that'd be greatly appreciated. If you need to reach out to us, please feel free to contact us via the email addresses shown, or alternatively through the website. I'll now pass over to 3 of my colleagues, Adam Price, Ryan Jones, and Jon Gannett, who are also senior METs with Glencore Technology. And they will run through some of the questions that were raised today and answer these live. Thank you.
Thank you very much, Matt. My name's Adam Price. I'm a senior MET that mainly looks after the Jamison cells at Glencore. Thanks very much for all the questions that came through today. If we didn't get to your questions, be aware that we will endeavour to do these via email. If we didn't get to them in time. Again, thanks for the questions. There was a good one coming from Tony Robbins. He was just asking about the air, and particularly the air to concentrate, how that'd be controlled and what sort of froth volume factors we'd be expecting for a project like Osorno. Froth volume factor is extremely important to consider in any lead zinc operation, particularly the zinc side of things can create some very tenacious froths. You can see froth volume factors as high as 2.5, even up to 3 and can become very difficult to pump. So this is definitely something we've taken into consideration for the design of the circuit, and we'll actually introduce one of our new technologies into the circuit design, and that is our froth pumps. These have been specifically designed with our other Glencore lead zinc sites in mind, and they have been operating there for quite a while to assist with pumping and removing the air out of these really tenacious froths. So with the Ozorne project, we'll include these froth pumps at key points through the circuit, obviously on all of the main concentrator pumps, to make sure that we don't have any issues there with pumping some of the tenacious froths, and we make sure that we can target the grades and recoveries we need to at all the certain sections of the plant. So we don't want any restrictions when it comes to pulling the amount of concentrate we need, and these froth pumps will be a key to making sure that we don't have any troubles there. So thanks again, Tony, for your question. I'll now pass it on to Jon Gannett to answer another question for you.
Thanks, Adam. We just got a question come through regarding the new layout for the isomill. And the question was, how is media collected in the new design after it's open for maintenance? This is an excellent question, and this is something that's allowed us to change our footprint design. We recognized during the maintenance shutdown that the rotor creates a bit of back pressure in the feed, and this back pressure, while allows the mill to run, could be used for discharging the mill. So by using this rotor for a designated amount of time, it pushes media back along through a designated port on the scuttle and back to the media hopper on the side of the bin. And by doing this, it allowed us to drop it from about 2 stories down to 1 meter off the ground. Thank you for the question, and I will pass it along to Ryan to answer the next one.
Great, thanks for that, Jon. Yes, so we got a lot of questions coming through, so I do apologize. We haven't been able to answer all of them, but we will get back to you on the ones that we haven't answered. One that came through from Ramat Hidiat. He's asking about the maintenance of the Jamison cells, I presume, but so he's asked what about the maintenance, what do we need to be aware of during operational? So, you know, maintenance on the Jamison cell is actually very simple. Most of it can be done while the plant is operating. So that's inspecting the downcomers, clearing the nozzles or measuring the nozzles, replacing the nozzles if need be, but they're not typically very high wear components, but that can be done while the plant is operational. So, you know, when you actually do need to do maintenance, things to be aware of is during a plant shutdown, you don't actually require a crane. So a lot of the time, a crane is it's a scarce commodity during a shutdown with the various foremen requiring the same crane at the same time. You don't have those sort of problems because you don't have rotors and stators and motors that you need to lift up and put into the Jamison cell. So maintenance is very simple, and we only have good things from our clients where they typically run the Jamison cells and don't have to give them much attention afterwards. Okay, thank you for that. I'm handing now over back to Erica, I believe.
Thank you, Glenn and Matt, for such a great presentation. And also thank you to our special guest, Alexander Kanarski. Thank you to Anya and our panelists, Adam, Jon, and Ryan, for assisting during the Q&A time. As previously mentioned, in the following weeks, you will receive an email with all the answers to your questions, the link to the calculators, and also the link to the recording. But before we close the webinar, Glencore Technology will be presenting a 2-day workshop at SIM conference where you will learn more in depth about the basic and design principles on isomill and Jamison cell. These workshops will take place on the 28th and 29th of April from 2 to 6 p.m. Canadian time. It is free to register. You only need to log in or create an account with SIM to access the free workshops. I think this is all for today for us. Thank you and see you at the next webinar.